Today, I will actually extremely happy to have Meigan Aronson. I tried to invite her, a couple of times, but this time that she finally agreed on a set date, and she will be talking about towards 1D heavy fermions, and she will have a 1 hour, and she will spend 20 to 30 minutes, give a very broad introduction. Yeah, welcome. Yeah, Meigan.
Well, thank you so much for the invitation, Peng Cheng, and it's wonderful to see so many friends here today. And to have this opportunity, of course, to say hello from Vancouver and to tell you something about our recent work, which I have entitled Towards 1D Heavy Fermions. And so I would I'll start, as Peng Cheng suggests, by talking a little bit about what is the motivation for this work, in particular the idea of 1D heavy fermions, and then tell you about our work to realize that kind of a system. Let's see. Interesting. Oh, there we are. Anyway, so of course I have the pleasure to be part of this team that I'm showing here. Xiang Li is a former postdoc. He's now at the Institute of Physics in Beijing. And Alberto Nocera is a colleague at the Quantum Matter Institute here at UBC. Katerina Foyetseva is currently at Notre Dame. She and George Savatsky provided important insight on the magnetism in this system using DFT. Of course, my longtime collaborator, Igor Zalesniak from Brookhaven. I want to start by comparing the very different descriptions of magnetism that we have in metals and in insulators. That is, I think, key to what we already know is the physics of heavy fermions that we hope to reproduce in a 1D system. And so specifically, there are two different paradigms, and in metals, we have an exchange interaction between the conduction electrons and the local moments called J-condo. And it does two things. On the one hand, it can it can make the conduction electrons of the local moments be anti-parallel and to form a singlet below a particular temperature called the condo temperature, given here in terms of the exchange coupling. At the same time, this interaction also leads to the coupling between magnetic moments via the RKKY interaction. And this leads to magnetic order, at least in the mean field, which is quadratic with respect to that exchange coupling. So Doniak was the first person to, I think, popularize the view that it's the tension between magnetic order and condo interactions that leads to this phase diagram that I've reproduced here at the bottom of the page as a function of temperature and JK. And so specifically, the magnetism is strongest at the smallest value of J, since it's quadratic with respect to J. So we expect magnetic order. And on the other hand, if we get to large values of J, instead we get strong condo screening where the magnetic moments are no longer available for ordering and purely a metallic state. And so there should be some sort of a value of the J condo where we can pass between those two limits at what we call a quantum critical point, if that happens at 0 temperature. And so just to drill down a little bit deeper on this, we imagine that we start at high temperature with conduction electrons, and we are coupled then to these local moments. And if the coupling is small compared to the thermal energy, we'll have a paramagnetic behavior. But as we lower the temperature, there are essentially two paths. One is that the magnetic moments will themselves couple magnetically, and they do that independently of the conduction electrons. So we arrive then at the lowest temperatures with magnetic moments that have ordered. On the other hand, there are systems in which, as we cool down, the strongest phenomena is the condo effect. So the magnetic moments are compensated at high temperature, and in this way they are incorporated into the Fermi surface itself, and we arrive at low temperature with these compensated moments that are retained only as correlations in a metal. And so there should be some value of that condo coupling in which we pass between these two phenomena at low temperature. This quantum critical point, where we have just balanced condo coupling, has strong effects on the properties of materials that form near these quantum critical points. And in general, one can use pressure or field or composition to tune that magnetic order to zero, where we call it the quantum critical point. And so I'm going to describe some of these phenomena using the famous system ytterbium-rhodium-2 silicon-2. Its phase diagram is shown here at the right as a function of temperature and field, and it's antiferromagnetic, just below 100 millikelvin, and a small field is required to suppress it to zero, near about 60 millitesla. Interestingly, at even lower temperatures, below 2 millikelvin, this system is superconducting. So in contrast to a normal metal, where we see Fermi liquid properties, in this system, we see non-Fermi liquid properties, which are evidenced by a resistivity which is linear with respect instead of quadratic, and as I've indicated here, and that if we also, and if we for instance, were to look at the resistivity, and this is a plot of the power law dependence. The orange region has resistance which is linear with respect to temperature, and the blue is resistance that is quadratic with respect to temperature. And you can see that the linear resistivity is largely found here near the critical field, whereas at higher and lower fields, the Fermi liquid behavior of the normal metal is retained. If we now imagine that we cool down in the Fermi liquid towards this critical point, I plot here the magnitude of the t-squared term, and you can see that it diverges as you approach the critical field. And this is suggestive then that the mass of the quasi-particles is increasing or becoming increased, and the quasi-particles are becoming increasingly localized as we approach the critical field. And finally, of course, that these seem to be part of the ingredients that are needed to realize emergent phases, in this case, superconductivity. So I think it's fair to say that there has been a lot of experimental and theoretical work that has gone into trying to understand the behavior near the quantum critical point in these systems, in particular beyond the simple description of the Doniak phase diagram that I've suggested. And I think it's largely believed that it's some mixture of the frustration of magnetic order by quantum fluctuations, by condo breakdown, or perhaps it's impossible really to separate the two of them in general. So this is a picture that is very different to the phenomenology that you would have in terms of insulators, which I'm going to sketch here. Here, the underlying model is the Heisenberg Hamiltonian, and it involves exchange coupling between the local moments, one or more of them, that could lead to ferromagnetic or antiferromagnetic order. And in the mean field, the ordering temperature is quadratic with respect to that exchange coupling. So you can see immediately the difference is that one way to getting a quantum critical point in these systems is not to decrease the coupling to zero, but rather you have to turn to the introduction of new kinds of interactions that would lead to quantum fluctuations, and in this way to frustrate the magnetic order so that it is confined to being at zero temperature. There are several ways you could do that. One is by geometrical frustration, as in this Pyrochlor lattice that I'm indicating. Another is through dimerization, as in the Shastry-Sutherland lattice. But I'm going to focus in this talk on low dimensionality, and in particular on the spin half chain that I've depicted here. And so in sort of the most basic sense, our work is aimed to try to bring insulators and metals together at the Hamiltonian level. And so the spin chain systems, I think, are particularly useful in this context because they have a well-established and well-tested theoretical framework. And that's evidenced here in this plot at the left, which is copper sulfate. These are neutron scattering results on the left, which show the excitations as a function of energy and momentum. And on the right are the results of DMRG calculations. And you can see that there's very good agreement between the two of them, and that the excitations that are being looked at here are fractionalized excitations known as the spinons. And so there's relatively little theoretical work which seeks to take an insulating system like copper sulfate and add conduction electrons to it. And here is an example from this very nice paper by Danu, where he proposes a particular Hamiltonian that has both Kondo coupling as well as Heisenberg coupling in it. And this is meant to realize a chain of Heisenberg atoms on top of a two-dimensional Dirac semimetal. And so the questions then would be, if on the one hand we have the fermions, which are the conduction electrons, and the spins on the other hand, the questions are, how do they change from their behavior as separate entities, and could we imagine that there were new sorts of order or even emerging states that would be possible at low energies and potentially at low temperatures? So interestingly, this system has already been realized in STM experiments, and that's here's an illustration from this very interesting paper, where you can see both the cores as well as the Kondo compensated moments for a chain of atoms that are placed on a metallic surface. And so Banu has provided a theoretical context for this work and essentially has shown that you need to have, not unreasonably, a large value of the Kondo coupling comparable to the Heisenberg coupling in order to see this line of critical points that separates, on the one hand, a Kondo singlet state from, on the other hand, a state which has individual spin chains. And so this is, in some sense, exactly what we are after when we try to find a new material where the spin chains are coupled relatively strongly to the conduction electrons. So we undertook a process where we tried to specify such a material, and we ended up with titanium-4 manganese bismuth-2, a material which continues to intrigue. And our claim is that this is a spin-a-half chain system that is manifestly metallic. And so here's the structure of this material, and you can see how important the chain, and I guess I've made this illustration to emphasize the chain-like character. These are manganese chains, and you can see that they're relatively well separated by about 7.4 angstroms in the bulk. And that the distance between the manganese atoms along the chain is 2.5 angstroms. That part is no coincidence in that we were aware that in other manganese intermetallic compounds, there's a crossover at about 2.65 angstroms between having well-localized manganese d electrons, if they are far separated, versus strongly hybridized and metallic manganese atoms for smaller spacings. And 2.5 angstroms is relatively close to that crossover. So what did we get? Did we get metallic moments, or did we get moments as in an insulator? And so the answer comes from looking at the magnetic susceptibility. This is actually the inverse susceptibility, and the black line is the Curie-Weiss fit. And what we found is that the moment per manganese is actually 1.72 Bohr magnetons, just as you would expect for spin-a-half. The Weiss field is antiferromagnetic, and it gives you an exchange of about 13 Kelvin or 1.1 millivolts, so quite small. Of course, the acid test for metallicity is, of course, the resistivity, and that's plotted here. You can see it's manifestly metallic. It has quite a large residual resistivity, but this number is relatively insensitive to sample disorder. And I finally want to mention that despite the one-dimensionality, we see little anisotropy in the resistivity, depending on if the current is along the chain direction or perpendicular to it. I'd like to talk a little bit more about how the crystal structure leads to the magnetic structure in this slide. In doing that, I'd like to think about the chemical environment of the manganese atoms that are shown here. So if you're this manganese atom, you look up and you see a square of titaniums. You look down, and you see another square of titaniums, and they are rotated 45 degrees with respect to each other. And so this means that the unit cell actually has two manganese, as I've indicated here, and it is the constructive and destructive interference of the d electron states for the titanium and for the manganese, which leads to these quasi-localized states, molecular orbitals that I'm showing here, which have a titanium part and a manganese part, like this. These orbitals have a lowest energy state which contains one electron, and so this is the origin of the spin 1/2 in this system. These magnetic orbitals are also alternate in, say, plus minus, as I've indicated here. And this suggests to us that we should be able to describe the magnetism in this system using a very simple frustrated model, where we have that the near neighbors are coupled ferromagnetically, and this is a consequence of the Hund's coupling that is found in this system, while the second neighbors are coupled antiferromagnetically. And we know that because of the Weiss temperature and as well the absence of any ferromagnetic order in the system. I'll show you, I'd like to start by talking about the conduction electron part, the fermion part of the problem. And I'd like to argue from this that this material that has actually relatively strong coupling between the conduction electrons and the local moment. To show you that, I've plotted here the resistivity as a function of temperature again, and the specific heat divided by the temperature to show that there's a regime in the material where we have Fermi liquid behavior, that is conventional metallic behavior. So below 77 degrees, we get a quadratic temperature dependence to the resistance with a certain magnitude. And at low temperatures, C over T becomes a constant, as we would expect for a Fermi liquid. And if we compare this constant to the square of this one, we get a particular quantity called the Katawaki-Woods ratio, and that is what is displayed here at the right. This is our material, titanium 4 manganese bismuth 2, which is compared to bona fide three-dimensional heavy fermion compounds here. You can see that it's clearly not as interacting as those compounds, but it is as strongly interacting as some ruthenates and cuprates, metallic ruthenates and cuprates, which indicates that there's a relatively strong degree of coupling between the moments and the conduction electrons in this system. So I'd like to turn now to the spin 1/2 character, and that's shown on this slide. And as I showed you when I discussed the structure, the Hamiltonian is suggested by that structure in that it has a ferromagnetic first neighbor interaction and an antiferromagnetic second neighbor interaction, and both are allowed to be anisotropic. And so we've carried out inelastic neutron scattering measurements that are shown here. This is the intensity of scattered neutrons as a function of energy and of wave vectors along the chain. And this is for wave vectors perpendicular to the chain. So you can see by inspection that these are one-dimensional excitations because you have dispersion only along the chain and not in the perpendicular direction. We used DMRG calculations to simulate or to calculate the dynamic structure factor. We got the best description of the data using J2 and J1 are approximately equal to each other, a little bit these are the values of the parameters. And as well, we found that the moments were modestly Ising-like and aligned along the axis of the chain. And the underlying antiferromagnetic structure, which hosts the spinons and the other excitations, at least at zero field, is an up-up, down-down antiferromagnetically ordered. So this is this is a qualitative description of the scattering, and this is a cut at q equals 0 to show you the extent of agreement between the DMRG and the experimental results, and I think you'll agree it's quite good. One thing I have to tell you, though, about this is that we've had to introduce some broadening to the DMRG. Ordinarily, we would take the resolution of the instrument itself, which is about less than 0.1 millivolts for this particular spectrometer, but we had to increase it by about a factor of 3 in order to match the DMRG to the data. So there is some anomalous broadening that's present here in this system, potentially due to the conduction electrons. And finally, I would say that high resolution DMRG experiments find that there's a small gap of about 0.3 millivolts that's present in the DMRG, which is clearly not present in the inelastic scattering, presumably because of the broadening that I've just mentioned. So we can also determine the magnetic phase diagram for the Hamiltonian using the DMRG calculations, and that's shown here at the lower left. So this is a function of the moment anisotropy. So these are Heisenberg moments at the top and Ising moments at the bottom. And this is the relative strength of the antiferromagnetic and the ferromagnetic interactions. And what you can see is that when the ferromagnetic interaction dominates, we get a gapless ferromagnetic phase, which is replaced above some critical value of J2 over J1 with a gapped antiferromagnetic phase. And there's even a vector chiral phase here for small values of anisotropy. And fortuitously, this material actually lies very close to the intersection of all three of these phases. And that indeed does result in a relatively complex magnetic structure. And that's shown here at the right. And so, as I mentioned before, the magnetic moments are along the chain axis, and they're modulated with up, up, down, 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 as I've indicated here. But they also are not pure Ising, and so they're going to precess around the direction of the chain, where the upspins and the downspins have different senses of precession, as I've indicated here. And in fact, the magnetic structure can be best described as a double helix, where the upspins and the downspins occupy the two different counterwound helices, as I've indicated here. So quite a complex magnetic structure.
So is there any canting?
Is there canting? As far as we know, only the precession. So what's important to realize, of course, is that there's not really long-range order,
sure.
and that the elastic scattering shows that this ordering is constrained within the unit cell, more or less. But importantly, its wavelength is exactly predicted by the DMRG, which is how we identify it. But this is purely one-dimensional order, if you like. There's no interchain coupling as far as we can tell.
Thank you.
All right. So it's a very intriguing system that we've described here. And so, of course, you will want to ask yourself, what can you learn about physics from this system? In that it has the attractive features that there's a pronounced Ising character to the spin of halves, that the exchange interactions are profoundly frustrated. We found no evidence for interchain coupling that would lead to three-dimensional order. And of course, the energy scales all seem to be quite small. So perhaps the fields that we have in our laboratory will be sufficient to change things. And finally, there's always the possible role of metallic electrons, which remains unexplored. And so If we apply a transverse field, for instance, we are certain that at zero field that we'll have precession around the chain direction, just as we're certain at sufficiently high field that we'll have precession around the direction of the external field. And so the question then is, how do you go between those two very different states? So to start that discussion, I've plotted here the results of DMRG calculations. So this is the moment projected along the transverse field. The black data points show you how that moment grows even from zero field, but that it essentially saturates or undergoes a slow saturation above about 4 Tesla. If we look at the slope, the derivative of this magnetization, we see that there are two peaks in the susceptibility at 3 Tesla and at 4 Tesla, as I've indicated here. And that's why I've indicated that there are two quantum critical points here in the phase diagram that mark the transition from precession around the chain to precession around the moment. The last point I want to make here, which I think is a significant one, is that if we measure this magnetization in the laboratory, what we see instead is this red line, which tells us that the magnetization is in fact very far away from saturation. And so that's a substantial difference from the DMRG calculation. Oh, and of course that it's featureless. We don't see anything at 3 or 4 Tesla. Okay, so I want to start by looking at the 3 Tesla quantum critical point, which we believe corresponds to the collapse of the dipolar antiferromagnetic order that I told you about a few slides back. And so the quantity that we're going to track as the order parameter is the correspondence between the moments in this pair and in the subsequent pair. And if we plot that quantity as a function of the field in blue, you can see that it's relatively constant up to about 2 Tesla, where it drops suddenly and vanishes around 3 Tesla. By the same token, if you remember the small gap that I told you came from DMRG, that gap decreases and is extrapolated to disappear also at 3 Tesla. So what's the property of these correlations at the critical field? So I've plotted here that order parameter as a function of the distance along the chain. And interestingly, we see that there's a power law correlation that's found only at 3 Tesla, and it has a slope of about minus 0.2. That's very interesting, of course, because it suggests that these correlations then are related to a one-dimensional Ising critical point, whose exponent is a quarter, which is relatively close to the value that we found. So by means of illustration, I've plotted here DMRG calculations at 0 field, which you've already seen, and at 3 Tesla, which you haven't seen yet. Just to point out to you that two things happen from the perspective of the spinons. And the first is that this gap vanishes, as I've indicated over here, and as well that the scattering is significantly broader at 3 Tesla than it is at 0 field. And so this suggests to us then that the spinons are overdamped, certainly at 3 Tesla, but even possibly at 0 field, and that the spinon gap and the antiferromagnetic order have collapsed at 3 Tesla. So what's left behind then are only short-ranged, exponentially short-ranged antiferromagnetic and helical correlations, which are not significant with respect to the observables. And the point that I'd like to make at this point is that the up-up spins and the down-down spin pairs do not collapse at 3 Tesla, but survive. And so that would we could say that above 3 Tesla, that magnetically we would say this is some kind of fluid of these spin pairs. So the next part of the phase diagram I want to address is for fields above 4 Tesla. And here again, I'll make the argument that the DMRG and the neutron scattering data agree quite well with respect to each other. So to begin with that discussion, I've plotted here DMRG calculations, and in the top row, these are the this is the dynamic structure factor, which is parallel to the chain, and the excitations that you see here are magnons. They have this characteristic W shape, which is a consequence of the frustration between the ferromagnetic and antiferromagnetic interactions that I've mentioned to you before. And so these excitations near 4 Tesla are ungapped, but that as we increase the field further and further, you see that the gap grows approximately linearly with respect to field. The second row is the dynamical structure factor in the transverse direction. And we see something that's very different here. That is, you see a gapless excitation at 4 Tesla, which is a continuum centered around Q equals 0, which becomes increasingly gapped as you increase the field, as I've indicated here. I'm going to make the argument that these excitations are 2-magnon excitations, and that this continuum is best thought of as related to the probability of having 2 simultaneous spin flips. For instance, you would take these 2 spins and turn them into these 2 spins with the delta S of plus or minus 2. So I want to stress to you that the 2-magnon excitations are not dipolar. These are quadrupolar excitations. They require 2 spin flips to be happening simultaneously, and that the phase space that they occupy is determined by conserving the energy and momenta of the 2 magnons. And so that phase space is indicated in this figure over here at the right. And I would invite you to use your imagination to say that that has the properties that we expect for a 2-magnon excitation, for a continuum of 2-magnon excitations. So we turn now to the experiments. The top row shows you the results of experiments that we carried out on high spec at the spallation neutron source. And these fields are from 0 Tesla up to 14 Tesla, as I've indicated. And the bottom row shows the DMRG calculations that were composed of the 2 branches of the excitations that I showed you on the last slide. So what you can see is that the correspondence between the DMRG and the neutron scattering measurements is, again, quite reasonable. In that both the magnon and the 2-magnon excitations are evident in the neutron scattering as they were in the DMRG. And this plot at the lower right basically tracks the peak intensity for both of them. And you can see the solid blue here are at high fields. This would be the energy of the peak in the neutron scattering measurements, and you can see that it grows at with a slope which is essentially G equals 2. It's not so different, I would say, from what you find from doing the same fit to the DMRG for the single magnon excitations, and we see a much more strongly growing intensity for 2-magnon excitations, which are quite weak for the inelastic neutron scattering measurements, but quite discernible in the DMRG. And so we would argue then that the high field data are also quite well described by DMRG using the same parameters as we had in 0 field, but manifestly increased broadening as we go to higher fields. So that leaves only the fields between 3 Tesla and 4 Tesla. So I've left them for last because this is where things seem to really go off the tracks. Of course, I want to remind you that the difference between 3 Tesla and 4 Tesla is exactly 1 Tesla. This is a very small energy compared to the exchange interactions or to any of the other parameters in the problem. So it's surprising then that we see a very strong field effect in this limited range of fields. So I'll illustrate that here in these panels at the right. as I've pointed out to you, at zero field and at high field, there's very good correspondence between DMRG and neutron scattering results using the same underlying parameters for the Hamiltonian. It was surprising to us then that at 3 Tesla and at 4 Tesla, there's an almost complete disagreement between the DMRG and the neutron scattering results, which are plotted together. At the left is an overview of the data that we found, and these data were measured at the OSIRIS instrument at the ISIS neutron source in the UK. And so if we start at we see that at 3 Tesla, at 3.5 Tesla and 4 Tesla, that there is there are surprising changes in the energy at which we see the peak, and as well as we increase the field, that we see some broadening of these excitations with increasing amounts of spectral weight transferred to lower energies, giving you this growth in the quasi-elastic scattering that you see at the lowest temperatures. And so the fact that at between 3 and 4 Tesla, that we've broken this tie between the DMRG and the neutron scattering is not a comment about the DMRG or the neutron scattering for that to that end, but rather that the Hamiltonian that we have used is missing some crucial aspect, that there's some additional piece of the physics that has not yet been included. So just to summarize the results of the experiments at all fields, we've done a simple phenomenological model, which is because the scattering is so broad, we have just fitted it to this damped harmonic oscillator, which has two parameters. It has a width and it has an energy for the peak intensity. And so we've plotted them in here at the right. This is the energy for the oscillator. And at zero field, as I've stressed, the neutron scattering and the DMRG by design agree with each other. But the DMRG would say that the gap at the lowest energy is suppressed at 3 Tesla, and the peak energy for the spin-on spectrum actually, that energy goes to zero around 4 Tesla. On the other hand, we know at high field that the neutron scattering measurements and the 1 magnon excitations, which are dominant, agree with each other. But the surprise was that the neutron scattering measurements at intermediate fields measured on two different instruments are in complete disagreement with the DMRG, but only for this intermediate range of fields. And finally, to speak to the broadening that comes out of this analysis, that broadening is substantial, as I've argued, at low fields, and grows, increases by about 50% as we go to the highest fields. And I want to apologize that there's this is the full width, whereas I've spoken about the half width previously. So apologies for the factor of 2 that I just discovered. But the DMRG has excess broadening at zero field, which is at the level of the green line, whereas the resolution of the spectrometer, at least the high-spec spectrometer, is shown by the yellow line. And so we have to conclude from this heuristic description that essentially we have very strongly overdamped excitations, particularly at high fields, and that while under some circumstances we have correspondence between experiment and theory, that correspondence fails over an extensive range of fields. So up to this point, I've spoken largely about the magnetic moments. And so you're probably asking, where are the fermions in this? What do the conduction electrons think about high fields? Well, I guess they don't think, but how do they respond to them? And so I'm presenting here at the left the resistivity as a function of temperature. And this is a relative, as you can see, this is a relatively small contribution to the overall resistivity that we're discussing. But this is for fields from 0 field up to 14 Tesla, as I've indicated. And that while we have t-squared behavior at the highest temperatures, indeed at the temperatures that are indicated down here, we see a linear resistivity at the lowest temperatures, and that is present at every field. And so this is the temperature field plot that shows the region in which you see t-squared behavior and where you see linear behavior in the resistivity. And so it seems as if every field there is some degree of linear in temperature resistivity in this system. So the question is, would that be expected? We have seen linear temperature dependencies and resistivities near quantum critical points in a number of different kinds of systems. But the question is, if you had, as we do, three-dimensional conduction electrons with an embedded spin chain, would we also expect to see linear resistivity? And so I'd like to recommend to you this excellent work by Laura Klassen, and her figure is shown here at the top of the page. And in comparison to a three-dimensional system, one expects an enhanced scattering from hotspots on the Fermi surface of a system consisting of three-dimensional conduction electrons and one-dimensional spins, just as we have claimed we have with titanium 4 manganese bismuth 2. And as is stated here, the resistivity is linear with temperature due to a field-induced critical regime. And so that I think concludes the experimental part, and I will leave you just with this simple summary, which is that titanium 4 manganese bismuth 2 is a remarkable system, and we'd like to argue at this point that it is perhaps an example, a sole example of a system where you have chains of localized electrons giving you spin-and-a-half moments that are coupled to fully three-dimensional conduction electrons with a sufficient strength to change the properties of both the conduction electrons and the magnetic moments. To summarize on the conduction electron side, the evidence for the conduction electrons being modified by the spin chains would be the enhanced Katawaki-Woods ratio, that the correlations manifestly have to come from interactions between the conduction electrons and moments, and the linear resistivity that I've spoken about. And by the same virtue that the magnetic moments are manifestly affected because the description that you have in 0 field and at high field is satisfactory for a Hamiltonian, which ignores the conduction electrons. However, the breakdown of that description on the magnetic side of in the magnetic subsystem remains a mystery to us, in that clearly there's some sort of a hidden mode. So there's some sort of a mode coupling scheme which separates the neutron scattering from the simpler and limited DMRG calculations. There's the possibility that the condo coupling could play a role there, particularly if we include the presence of the critical excitations. And I think we're always just free to throw up our hands and say, quantum critical points, of course, have all manner of influences on the physical properties, and that there are more things that we need to understand about the system in this mysterious region between 3 and 4 Tesla. So thanks very much for your attention, and happy to try to address any questions that you might have.
Yeah, fantastic talk. Yeah. So any question? Laura's hand. Yeah. Oh, so there's a question from Lynn Rogan.
Mm-hmm.
Okay. Let me read. I guess can you just unmute and read yourself instead of for me to read?
Oh yeah, okay.
I'm sorry,
Yeah,
I can't.
I'm wondering, in your inverse magnetic susceptibility plots, the Curie-wise
Yeah.
fitting doesn't look quite linear at high temperature. Do you have any thoughts on why that might be?
Yes, I do. And so I think it's a shortcoming of the plot itself. I prefer to, plot 1 over chi minus chi naught versus t myself. I would refer you to our publication if you want to see a better plot of that linearity. So there's no deviation up to room temperature anyway with that linearity, in my opinion.
Okay, got it. And I have other question like, do you think the coupling between conduction electrons and local moments could affect the inelastic neutron scattering dispersion?
I think at a minimum, it provides the excess broadening. That is actually, I didn't mention it, but that is also something that Danu paper highlighted in terms of the so I think your question, though, is a deeper one, which is you're asking me, I think, to speculate on the differences in the Hamiltonian that could happen at intermediate fields. I wish I could tell you more. All I can say at this point is that it's something that is missing if we had a purely insulating system. And the description that we have so far is perfect for an insulating system, but it fails miserably due to some unknown circumstances at intermediate fields.
Thanks, Mel.
Okay.
Yeah, Meigan, beautiful talk. So I had two things in my mind. One is that, so I think we talked about this. Manganese for me is almost like really close to localized moment. And so from the perspective, say, critical behavior of resistivity and other indications, do you think it's very close to heavy fermion condo-like systems, or there's still some distance from it? I'm not sure how to quantify my question, but it's in my mind.
It's interesting. So the origin of as I said, the origin of the spin-a-half is not the usual picture where you have manganese D5, you have crystal fields, and you can determine what a spin is. Manganese spin-a-half is very, very rare, maybe even vanishingly rare, in that context. And so in our case, though, the manganese moment is manifestly the result of the overlap of other wave functions. And so it has an inherently delocalized character, which is inconsistent sort of with your expectations for what it should be, in an insulator. And so at the end of the day, I think that there is another degree of freedom, that we really haven't thought about too far, which is the extent to which we can manipulate those magnetic orbitals in a field. And so I have a suspicion that might potentially be part of the story. I think you might be asking really about the issue of condo breakdown and the extent to which that could be relevant in a system with manganese spin-a-half. I agree, it's a stretch, but you should perhaps remember, though, that if you think about all manganese metallic compounds, of which there are many, there are some with localized manganese moments and some that don't. And that was the point that I made about there being sort of a critical manganese distance where in the context of the Hubbard model, you go from having large U over T to small U over T and delocalization, according to, that kind of scheme.
Okay, yeah, that's great. Some things to further think about. The other question is more just experimental. So near the critical field, is there any indication of some sort of scaling in the dynamics?
So in the DMRG calculations, yes. And so in terms of the neutron scattering, all the experiments we've carried out so far have been at the lowest temperatures. So we do not know yet what the effect of temperature is, but I think that's clearly the next set of experiments, which would be to look for things like E over T scaling, for instance, for different values of the field, or T over H scaling for that matter.
Okay, great. Yeah, thanks.
Yeah, so Meigan, Laura, you have a question? Okay, so I have a question, Meigan. So So, I mean, one thing that you said is, it's a spin of half, but the object is actually very large, right? You emphasize very strongly. There's a strong hybridization between the titanium and also the manganese, right? So that basically means that in real space you have a composite spin of a half system instead of a small moment. So that in principle should show up in your magnetic form factor, right? And the distance dependence of a magnetic form factor. Have you actually seen that?
We have. So we see the normal manganese form factor, I guess, in the transverse direction, more or less. But we see so we see a much sharper fall off of the form factor along the chain direction than would be expected for an atomic form factor.
I see. But I mean, the key question I have is that when you apply an external transverse magnetic field, do you expect I mean, would there be possibilities for the orbitals to actually change directions, or is that a speculation?
That is definitely speculation, and I just maybe which we love speculations, but I would just remind you, look how sort of broad and weak the scattering is it is at the highest fields, and so so you'd basically be trying to fit a form factor to these data. So I think that the data at present really don't support that analysis, sadly. But
I see. So what is the conclusion? So what is the conclusive evidence for the cluster itself being a spin of a half object?
Well, I mean, fundamentally, I mean, you have to really struggle to find spin a half in a manganese system.
I know, that's what I mean, right? How do you assert that this is really sort of a quantum system? Meaning that the composite project is of a spin of a half.
Not sure how to answer that question. I mean, the DFT calculations basically revealed the constructive and destructive interference of the d electron, manifold that I spoke about, and so we don't know anything about their properties, the splitting of the different levels in the molecular orbital in a field. But I suppose you're not really asking me about that.
No, I'm asking an experimental question. Or maybe potentially one can do is that there's a business of a total moment sum rule, right? If you integrate the entire spectral weight, you can potentially see whether the total moment that's seen by neutron scattering is equivalent to actually a spin of a half system, because a spin of a half system, at least in the case of insulator, is well known, right?
Yeah. So I would say that the scattering that I present is actually in absolute units.
Yes.
And while I didn't show you those sum rules, they're in our paper, and we do moderately well. So I mean, I'm sure we have. I don't want to speak off the top of my head, but we are seeing most of the scattering. There's I don't think anything that we've missed.
Just can I follow up on that?
Yeah, sure.
So, so Meigan, I lost track. How big is the scale of the J's you extract? Are you covering pretty much the majority of the spectrum?
Yeah, this is a fantastic thing about this system. So let's see, J1 is around 3 millivolts and J2 is around 2 millivolts.
Okay.
So quite small.
It seems like Pencha is right. The information is in the data.
Right.
What about go ahead, sorry.
I mean, I think that we now know, having done the intermediate fields, that there's something really missing, and we didn't have that understanding at all, prior to that. And that was, of course, the last measurement that we did.
Okay, very, very.
But I was going to ask. I mean, you also have the Curie constant, right, from the susceptibility fit to the Curie wise plus some offset. Does that Curie constant give you some hint that it's spin 1/2?
Yes, that's exactly correct. We found that the Curie constant gave us a moment of 1.7 Bohr magnetons for manganese.
I see. There are additional questions from the web. So the question is it possible to see two magna excitations in inelastic neutron scattering?
Generally, no. Generally, no. And I guess that your ability to see them depends on several things. One would be the density of the magnons that you have, and essentially the likelihood that you would simultaneously create two individual magnons. And so we have to conclude that that is something that is quite likely. My personal belief would be that it reflects in the end of the day, it reflects Hund's rules in that we have these pairs of spins, and they're not like a dimer. In if you say that the rule is that they always there's always two spins parallel, anti-parallel to each other, then perhaps that is the origin, if you like, of the extreme health of two magnon excitations in this system.
Mhm.
I see. And there's another question.
Yeah.
I'm sorry. Kathy, you have a question?
Yeah.
Alan? Yeah, sorry.
Do you have density functional calculations in a magnetic field? I'm thinking that the mysterious thing that's lurking around here is the cluster character of the moments. And at field 0, you have some insight from DFT, and maybe DFT in a field would help you understand if something's going wrong with the cluster that's giving you the moment in this the field is messing around with the chemistry.
That's an excellent point, Jim, and I think that George and Katerina presumably will be interested in sort of taking that next step with their calculations, but it's possible that they're not really they have not yet been briefed on that.
Okay. George probably can't resist.
That is a true fact.
One last question, Meigan. By Lynn Rogan on the web, but has anyone done hyperscaling on the sample to extract a critical exponent in the vicinity of a quantum critical point?
You mean as a theoretical question?
No, experimental question. I mean, I get, yeah, hyperscaling. I get he means some sort of quantum critical scaling near. I mean, I think you answered that question, right? Basically, you only have done one temperature, right, so far.
Yeah, and that yes. So that's what's up next.
Yeah. Okay.
So Pinchen can still jump in unless somebody else has a question.
No. I mean, you have the right to jump in, Chimiao.
Thank you. So my questions are related to what was just asked, but also following up on the earlier question. So I was fascinated by that you showed the resistivity reacting to the quantum criticality.
Mm-hmm.
And so I wonder whether there's information on the converse aspect, which is you have the DMRG result for the low temperature frequency dependence of the dynamic or spin susceptibility, right? So in principle, one could compare what you measure in the frequency dependence with DMRG result to see how much of consistency or whether there is some additional features that could be due to the reaction from the conduction electrons?
That's quite interesting. My first response to that would be, though, that the linear resistivity is there at every field, and that the DMRG finds the spectrum to be gapped up to 3 Tesla, but not above. I mean, well, between 3 and 4 Tesla. I mean, that is a unique part of the behavior in that even the DMRG would say there's no gap only between 3 and 4 Tesla. So, I don't know. I'm gonna have to think about that. That's an interesting suggestion.
Yeah, thank you.
Maybe the specific heat actually at low temperature would have something to to say about
the combination. Yeah.
Right.
Okay. Yeah. Well, with that, thank Meigan again for a wonderful talk and wonderful discussion. Yeah.
Thank you,
Meigan.
and
Thank you, Meigan.
lovely to see so many of you.
Yeah, great talk. Thank you, Meigan.
Meigan,
Thank you, Meigan.
you really
Yeah.
done a fantastic job. You have like almost 60 people attending your seminar.
Oh, wow.
So very much enjoyed your talk. This is Tomo.
Yeah, Tomo Yomura. Yeah.
Oh,
Hey, how are you?
It was fun to hear an Aronson talk again. Made the day.
Oh, you mean you're thinking about her PhD thesis defense?
and not samarium hexaboride. So yeah, this was a great talk.
I'm sorry for that joke. Maybe not appropriate.
I don't mind inappropriate.
I have been here, but I arrived a little bit late.
Yeah, I would notice you're on. Okay.
That's the point. So I
Yes,
missed
middle of the night.